Welcome to This Explainer. Today, we're diving straight into what I'd call the ultimate cosmic mystery. We're going to look really closely at a question that has literally baffled scientists for decades. I mean, think about it. Why is gravity, the force that shapes our entire universe, inexplicably, almost laughably weak? So let's jump right in and look at the actual physics that make our reality tick.
Here is our roadmap for today. We'll start with the ultimate cosmic mystery, map out the four fundamental forces, tackle the hierarchy problem, look at the Higgs boson connection, explore the wild idea of gravity leaking into extra dimensions, and finally, look at the search for actual proof. All right, let's get started.
Section 1. The ultimate cosmic mystery. To really grasp the sheer scale of this problem, let's start with a physical demonstration you can actually do right now to experience this mind-bending physics paradox firsthand.
Okay, imagine picking up a piece of paper from your desk. You just lift it right up. Well, congratulations. You have just successfully counteracted the combined gravitational might of the entire planet Earth. When you easily lift that piece of paper, your hand completely overpowers the gravitational pull of 6 septillion kilograms of mass trying to hold that paper down. How is that even remotely fair? Like, why is it so incredibly easy for us to do that?
Section 2. The four fundamental forces. Now, to understand why this paper lifting paradox is so weird, we really need to establish the baseline of the universe's four fundamental forces.
When we look at data from MIT comparing the relative magnitudes of the forces acting on a pair of protons, it's pretty shocking. If we assign gravity a baseline strength of 1, it's the weakest force by an absolutely staggering margin. The next weakest is the weak nuclear force, and it beats gravity by a factor of 10 to the 24th power. That is a trillion times stronger. Then the electromagnetic force is a massive 10 to the 35th power times stronger, and the strong nuclear force takes the ultimate prize at 10 to the 37th. To put that into perspective, even if gravity were somehow a billion times stronger than it is right now, it would still be the weakest force by a billion times. No contest.
Looking at this in terms of quantum field theory and energy scales, there is an incomprehensible gap of 16 orders of magnitude. Yep, that is 16 zeros right there. That's the gap between the weak scale of particle physics, where particles actually get their mass, and the distant Planck scale, which is the massive energy realm of gravity. The fundamental principles of physics we have right now simply don't tell scientists how to transition smoothly across this massive gap.
Section 3. The hierarchy problem. This inexplicable weakness brings us to the absolute core conflict in modern physics.
The hierarchy problem basically asks why our standard model of physics provides absolutely no mathematical reason for gravity's relative feebleness. There's this massive hierarchy between the weak scale and the Planck scale. Just as physicists literally have to plug particle masses into the standard model by hand, they have to construct these energy scales by hand too. Why? Because the math doesn't naturally spit out an answer for why gravity is so incredibly weak.
When we compare the interaction of electromagnetism to gravity, we run into a massive mathematical headache. Because gravity operates at that distant Planck scale, trying to calculate the single graviton exchange at high energies completely breaks our equations. I mean, the math just spirals totally out of control, generating these infinite numbers that make predictions completely impossible. It is a literal mathematical brick wall.
Section 4. The Higgs boson connection. So how does standard physics actually try to explain this? Well, if there's nothing wrong with gravity, maybe the answer lies with the other forces. Let's see how they explain why the weak nuclear force is so much stronger. It turns out it all comes down to the mechanics of the Higgs boson. This might build a potential solution. The Higgs field essentially soaks all of space-time and forces particles to acquire mass. The more something interacts with the Higgs, the bigger mass it gets. So the crucial point is how this works in practice. You've got the W and Z bosons, which are the force carriers of the weak nuclear force. They acquire their mass by interacting with the Higgs boson. Therefore, the properties of the weak force are entirely dictated by the mass of these W and Z bosons, which is inherently tied to the Higgs mass. And here is the kicker. The Higgs mass is oddly fine-tuned. A naive quantum understanding suggests the Higgs mass should either just cancel out to zero or balloon all the way to infinity. But instead, it sits precisely fine-tuned at an acceptable range. So the weak force appears so much stronger because the Higgs boson is mysteriously fine-tuned to keep the W and Z bosons at tiny mass values. Basically, the weak force is kind of cheating. Gravity isn't weirdly weak, the weak force is just artificially strong.
Section 5. Leaking into extra dimensions. But what if we're looking at this whole shebang wrong? What if gravity isn't actually weak at all?
and we're just looking at the universe from a terribly limited perspective.
Enter string theory and the ADD model, named after physicists Arkani-Hamed, Dimopoulos, and Dvali. This model introduces a complete, mind-blowing paradigm shift. It proposes that our universe, with its three spatial dimensions and time, actually exists on a membrane, or a brain, in a much higher dimensional space. The electromagnetic, strong, and weak forces, they are hopelessly trapped on this 3D brain, but gravity, and its hypothetical carrier particle, the graviton, can actually propagate across the full spacetime, leaping out into the higher extra dimensions, which physicists call the bulk.
Because gravitons can just wander away into these extra dimensions, much of gravity's attractive power literally dilutes or leaks away from our observable universe. If the power law of gravity changes out there in these extra dimensions, the fundamental scale of gravity could be brought down all the way from the distant Planck scale to the weak scale, which is right around 1 tera-electron-volt, or TeV.
To put it plainly, gravity is actually an absolute powerhouse. It is simply forced to spread its immense strength across a much larger, multi-dimensional canvas. It only appears weaker to our limited three-dimensional experiments. It's like pouring a cup of water into a pool instead of a small bowl. It's the same amount of water, it's just spread out way too thin for us to notice its full depth. Section 6. The search for proof. Now, that is a beautiful theory. But in physics, beautiful math just isn't enough. So how do we physically prove a theory about invisible extra dimensions?
Well, scientists are actively putting this to the test right now. Over at the Large Hadron Collider, they are violently colliding protons together. The idea here is that if a graviton is formed in the collision, it could literally propagate out into an extra dimension. If it does that, it'll carry energy with it, leaving a detectable imbalance of transverse momentum in our 3D detectors, basically missing energy. Scientists are also testing gravity at sub-millimeter scales, looking for gravity to suddenly act much, much stronger, because at that tiny distance, it hasn't had a chance to leak out into the bulk yet. We're talking right at the scale of your fingertips.
Okay, here is where it gets slightly terrifying, but also incredibly exciting. If the fundamental scale of gravity is actually much lower than we thought, like down in the TeV range instead of the massive Planck range, then advanced colliders might actually possess enough energy to squash particles together and form tiny short-lived black holes right there in the lab. If we saw that, it would be absolute definitive proof of large extra dimensions.
So, I want to leave you all with this thought. We walk around every single day effortlessly defying gravity, entirely unaware of the cosmic mechanics allowing us to do so. It really leaves you to look at empty space differently, doesn't it? Just wondering what mind-bending higher dimensions might be secretly draining gravity's power just a fraction of a millimeter away from your own hand. Thank you so much for joining me for this explainer, and remember to keep questioning the universe around you. Catch you next time.